Good evening and welcome to Dreamy Academy. Tonight, we turn our gaze inward, embarking on a journey into the most intricate and enigmatic structure known to us, the human brain. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. Imagine for a moment the vastness of the cosmos we sometimes explore together. Galaxies swirling with billions of stars, each a sun unto itself. Now consider that within the quiet confines of your own skull, there exists a structure of comparable, perhaps even greater complexity. A universe of electrical impulses and chemical whispers housed in a 3-pound organ that fits in the palm of your hand. This is the brain, a realm where matter has learned to contemplate matter, where the universe looks back upon itself and asks questions of its own existence. It is here that your dreams take flight, your memories are sculpted, and your very sense of self resides. Every thought you've ever had, every emotion you've ever felt, every word you've ever read, every sound you've ever heard, all of it is born from the ceaseless silent ballet of countless tiny cells, firing and connecting, weaving a tapestry of consciousness. This isn't a simple machine. It's an evolving, dynamic landscape shaped by every experience, every interaction, every moment of your life. To understand it is to glimpse the profound elegance of biological engineering refined over eons, and to touch upon the deepest mysteries of what it means to be alive, to be aware. There is a deep, quiet wonder in realizing that the very organ processing these words, creating meaning from sound, is itself the subject of our contemplation. It is a mirror reflecting its own intricate design, a paradox of astonishing beauty. Let's begin by considering the fundamental building block of this inner universe, the neuron. Picture, if you will, not a simple spherical cell, but a tiny, elegant tree, reaching out with delicate branches and roots, constantly listening and speaking in a language of electrical pulses. This is the neuron, and within your brain there are approximately 86 billion of them. 86 billion, each one a microscopic marvel forming connections that dwarf the number of stars in our galaxy. Each neuron is a specialized cell exquisitely designed for communication. It has a central body like the trunk of our imagined tree, called the soma. This is the neuron's metabolic heart, where the nucleus resides, directing the cell's life processes. Extending from the soma are the branches, thin tree-like structures called dendrites. These dendrites are the neuron's primary receivers. They are adorned with tiny receptors, constantly sampling the chemical messages sent by neighboring neurons, like delicate antennae sifting through a silent broadcast. Think of them as listening posts, gathering information from thousands of other cells, taking in a chorus of whispers and shouts. If a neuron receives enough signals, enough whispers and shouts reaching its dendrites, it might decide to speak, and when it speaks, it does so through a single, long, slender projection called the axon. This axon is the neuron's dedicated transmission line, extending away from the soma, sometimes for mere micrometers, sometimes for a meter or more, reaching distant parts of the brain or even down into the spinal cord. The axon ends in a series of smaller branches called axon terminals, each tipped with a tiny bulb. These bulbs are the neuron's mouthpieces, poised to release chemical messages to the dendrites of the next cells in the chain. So a neuron listens with its dendrites, processes in its soma, and speaks through its axon. It is a beautifully efficient one-way street of information flow, designed for speed and precision. The true marvel, however, lies not just in the neuron's structure, but in its very nature as an electrical entity. These cells are not simply passive wires, they are living batteries, constantly maintaining a delicate balance of electrically charged particles, or ions, across their membranes. Imagine a tiny invisible wall, permeable to some ions but not others, carefully controlled by microscopic gates. On one side of this wall, inside the neuron, there's a slightly negative charge. On the outside, a slightly positive charge. This difference in electrical potential is called the resting potential, and it's what gives a neuron its quiet readiness, its potential to spark to life. It's like a coiled spring holding energy, waiting for the right moment to release it. When the dendrites receive enough excitatory signals from other neurons, those delicate gates in the membrane begin to open. Charged ions rush in, momentarily flipping the electrical balance. This rapid, dramatic shift from negative to positive inside the neuron is called an action potential, the neuron's electrical spark. It's a sudden, fleeting surge of electricity, lasting only 1,000th of a second, but it's powerful enough to trigger the next set of gates along the axon. Like a domino effect, this electrical pulse travels swiftly down the entire length of the axon, maintaining its strength without fading. It's a digital signal, an on or off message, unambiguous and clear. This is the language of the brain. Billions of these tiny, precise electrical flashes racing along neural pathways, carrying information about everything from the warmth of your breath to the memory of a distant summer day. At the very end of the axon, where it meets the dendrites of another neuron, there's a tiny gap, a space almost unimaginably small called the synapse. The electrical signal cannot simply jump across this void. Instead, the arrival of the action potential at the axon terminal triggers a beautiful chemical dance. Tiny sacs, filled with specialized chemical messengers called neurotransmitters, migrate to the edge of the terminal. Upon the electrical signal's command, they fuse with the membrane and release their precious cargo into the synaptic gap. These neurotransmitters diffuse across the space like microscopic boats sailing to the other shore, where they bind to specific receptors on the dendrite of the receiving neuron. This binding is the key. It's like a lock and key mechanism, exquisitely specific. Depending on the neurotransmitter and the receptor, this chemical message will either excite the receiving neuron, making it more likely to fire its own action potential, or inhibit it, making it less likely to fire. It's a system of subtle persuasion, of encouragement and dampening, creating complex patterns of activation and silence. This dance of electrical impulses giving rise to chemical signals, which then give rise to new electrical impulses, is the fundamental rhythm of your brain. It is how the information is encoded, processed, stored and retrieved. It is how your perception of the world is built, one tiny, precise chemical electrical exchange at a time, echoing through vast networks of interconnected cells. The elegance of this system lies in its sheer numbers and its dynamic nature. Each neuron, receiving input from thousands of others, acts as a tiny decision maker, integrating all the incoming signals before deciding whether to send its own message onward. These decisions, aggregated across billions of neurons, create the emergent phenomena we call thought, emotion, and consciousness. What we are witnessing at this microscopic scale is the very foundation of your internal world, a silent symphony of activity that allows you to read these words, to understand them, and to feel the gentle drift towards sleep. We left off marvelling at the sheer elegance of billions of decision-making neurons, their individual electrical sparks and chemical whispers culminating in the grand tapestry of thought, emotion, and consciousness. But how, you might ask, do these billions of individual conversations coalesce into a coherent narrative, into the very story of you? It is here, my dear friends, that we must turn our gaze to the silent, intricate symphony orchestrated by the very chemical messengers we briefly touched upon, the neurotransmitters. Imagine, if you will, that the electrical impulse travelling down a neuron's axon is like a swift, urgent message carried by a courier. When this courier reaches the end of their journey, at the synaptic terminal, they don't simply shout their message across the void. No, they release specialized envelopes, each containing a specific kind of chemical note. These are our neurotransmitters, the exquisite language of the brain, allowing neurons to communicate with astonishing precision and diversity across that tiny, yet profoundly significant synaptic gap. Each neurotransmitter is a unique key, designed to fit a specific lock, a receptor, on the neighbouring neuron's dendrite. This lock and key mechanism is fundamental to how information is processed and how our brains differentiate between a myriad of signals. It's not just a matter of on or off, it's a nuanced conversation, rich with context and consequence. Let us explore some of these chemical messengers, for they are the very architects of our inner world, shaping our moods, our memories, our movements, and even our dreams. First, consider glutamate. This is the brain's primary excitatory neurotransmitter. Think of glutamate as the accelerator pedal of the brain, pushing neurons toward firing an action potential. It is absolutely vital for learning and memory formation. When you are absorbing new information, when you are recalling a cherished memory, it is glutamate that is busily strengthening the connections between neurons, carving new pathways in the intricate landscape of your mind. Without glutamate, our ability to learn, to adapt, to form new experiences would be profoundly diminished. It is the enthusiastic "yes, let's go" in the brain's continuous dialogue. On the other side of the coin, we have GABA, gamma-aminobutyric acid, the brain's main inhibitory neurotransmitter. If glutamate is the accelerator, GABA is the brake. It slows things down, calms neuronal activity, and helps to maintain a delicate balance within the brain's bustling networks. Imagine a busy city at rush hour. GABA helps prevent gridlock, ensuring that the flow of traffic, of information, remains smooth and controlled. It reduces anxiety, promotes relaxation, and helps us sleep. A healthy balance between glutamate and GABA is essential for preventing overstimulation, which can lead to seizures, and for maintaining overall mental well-being. It is the gentle "let's pause for a moment" that brings order to the potential chaos. Beyond these fundamental excitatory and inhibitory roles, we encounter a fascinating array of modulatory neurotransmitters. These chemicals don't just directly excite or inhibit a single neuron. Instead, they act more like conductors of an orchestra, influencing the overall tune or mood of large groups of neurons. Take dopamine, for instance. This neurotransmitter is often associated with pleasure, reward, and motivation. It's the chemical surge you feel when you achieve a goal, when you experience something enjoyable, or even when you simply anticipate a reward. Dopamine helps us focus our attention, drives us to seek out new experiences, and plays a crucial role in motor control. Picture it as the brain's internal spotlight illuminating what is important and compelling us to act. It's the "I want that" or "let's do this again" signal that shapes our desires and our pursuit of happiness. Imbalances in dopamine are implicated in conditions ranging from Parkinson's disease, where dopamine-producing neurons degenerate, to addiction, where the reward pathways are hijacked. Then there is serotonin, a neurotransmitter often called the feel-good chemical, though its roles are far more complex and pervasive. Serotonin profoundly influences mood, sleep, appetite, digestion, learning ability, and memory. It helps regulate our emotional states, contributing to feelings of well-being and contentment. Think of serotonin as the brain's internal thermostat for mood, working to maintain a stable and comfortable emotional temperature. When serotonin levels are out of balance, it can significantly impact our emotional landscape, contributing to conditions like depression and anxiety. It's the subtle hum of contentment that underlies our daily experience. Acetylcholine is another remarkable player. It is critical for muscle contraction. Every time you move a muscle, from blinking your eye to running a marathon, acetylcholine is at work at the neuromuscular junction. But its influence extends deep into the brain, where it is vital for attention, learning, and memory. It's like the brain's internal focus switch, helping us concentrate on tasks and consolidate new information into lasting memories. The degeneration of acetylcholine-producing neurons is a hallmark of Alzheimer's disease, underscoring its profound importance in cognitive function. And let us not forget norepinephrine, which also acts as a hormone and is intimately involved in our fight-or-flight response. Within the brain, norepinephrine plays a key role in alertness, arousal, attention, and the regulation of sleep-wake cycles. It's what sharpens your senses and prepares your body for action when you perceive a threat or need to be highly focused. It's the internal alarm system that snaps you to attention, heightening your awareness of the world around you. As these diverse chemical keys are released, they traverse the synaptic cleft, binding to their specific receptor locks on the postsynaptic neuron. This binding event triggers a change in the receiving neuron, either pushing it closer to its firing threshold, excitation, or pulling it further away, inhibition. The beauty lies in the swift, precise termination of these signals. Once a neurotransmitter has delivered its message, it doesn't linger indefinitely. It is either rapidly reabsorbed back into the presynaptic neuron, a process called reuptake, or broken down by enzymes in the synaptic cleft. This meticulous cleanup ensures that the next signal can be sent clearly and efficiently, preventing a constant, overwhelming cacophony of messages. It is a dance of exquisite timing and perfect execution. Now, consider the individual neuron receiving hundreds, even thousands of these chemical whispers simultaneously from countless other neurons. Some messages are excitatory, urging it to fire. Others are inhibitory, telling it to hold back. How does a single neuron make its decision? It's a continuous, complex calculation, an intricate summation of all incoming signals. If the combined excitatory signals outweigh the inhibitory ones and reach a critical threshold, then and only then does the neuron generate its own action potential, sending its electrical spark onward. This sophisticated decision-making at the microscopic level forms the very foundation of neural networks. Imagine a single conversation, then a small group, then a vast assembly, all interconnected and communicating. Neurons don't act in isolation. They form intricate circuits, pathways, and networks that specialize in different functions. There are networks for vision, for language, for motor control, for emotion, for memory, and for abstract thought. These networks are not static. They are dynamic, ever-changing constellations of activity. This brings us to one of the most astonishing properties of the brain: plasticity. The brain is not a fixed, immutable structure. It is a living, breathing, constantly adapting organ. Every new experience, every new piece of information you learn, every skill you acquire, subtly alters the physical connections within your brain. This phenomenon, known as synaptic plasticity, refers to the ability of synapses, those tiny gaps where neurons communicate, to strengthen or weaken over time in response to activity. Think of it this way. When two neurons frequently communicate, their connection becomes stronger, more efficient. It's like forging a well-worn path through a forest. The more you use it, the clearer and easier it becomes to traverse. This is often summarized by the adage, "What fires together, wires together." Conversely, connections that are rarely used can weaken or even be pruned away, like overgrown paths that fade back into the wilderness. This capacity for plasticity is why you can learn a new language, master a musical instrument, or adapt to new environments. It's why your brain can recover from certain injuries, rerouting pathways and creating new connections to compensate for damaged areas. It's the biological basis of memory, allowing us to store and retrieve vast amounts of information over a lifetime. It's the reason why your brain, right now, as you are reading these words and absorbing these concepts, is subtly reshaping itself, forming new connections and strengthening existing ones. Consider the profound implications of this. Your brain, the very seat of your identity, is not merely a static processing unit. It is a dynamic, living sculpture, continuously being molded by your experiences, your thoughts, your interactions with the world. Every moment of your existence leaves an imprint, however subtle, on the intricate wiring of your mind. You are quite literally a work in progress, an ever-evolving masterpiece of neural architecture. So when we speak of the brain, we are not just talking about 86 billion neurons. We are talking about quadrillions of synaptic connections, each capable of being strengthened or weakened, each a potential conduit for information, each contributing to the unique symphony that is your consciousness. We are talking about an internal universe where electrical impulses spark and chemical messengers dance, not in a chaotic frenzy, but in a meticulously orchestrated ballet of incredible complexity and astounding elegance. This continuous silent symphony of signals, where glutamate urges forward and GABA gently reins in, where dopamine motivates and serotonin soothes, where acetylcholine focuses and norepinephrine alerts. This is the foundation upon which your reality is built. It is the unseen engine of your thoughts, your feelings, your memories, and your dreams, and it is perhaps the most extraordinary testament to the profound beauty and enduring mystery of life itself. We are truly just beginning to appreciate the depth of this inner cosmos. Welcome back, dear friends, to the gentle embrace of Dreamy Academy. As the stars begin their silent dance across the velvet canvas of night, we turn our gaze inward once more, continuing our exploration of the most intricate universe known to us, the human brain. In our previous journey, we ventured into the microscopic world of neurons and the exquisite chemical ballet of neurotransmitters, witnessing how these tiny electrical impulses and chemical whispers form the very language of our inner world. We learned of the brain's breathtaking plasticity, its capacity to reshape itself with every experience, every thought, every feeling. But now I invite you to step back with me, to widen our perspective. Imagine, if you will, moving beyond the individual performers in this grand neurological symphony and beginning to appreciate the orchestra itself, the sections, the movements, and how their harmonious interplay creates the profound emergent phenomenon we call consciousness. We've seen how individual neurons communicate, how they fire together and wire together. But how do these billions of individual conversations coalesce into a unified experience? How do they give rise to our memories, our dreams, our sense of self, our very ability to perceive the world around us? The answer, in its simplest form, lies in the intricate architecture of neural networks and the specialized yet interconnected regions of the brain. We are not merely a collection of isolated cells. We are a vibrant, dynamic tapestry woven from countless threads of interaction. Each neuron, while possessing its own unique role, is part of a larger, functional circuit, a sophisticated network designed for specific tasks. Think of it as a vast living city, where individual citizens, neurons, perform their duties, but it is the organized districts, brain regions, and the intricate systems of roads and communication lines, neural pathways, that allow the city to thrive, to learn, to adapt, and to create. Our journey now takes us to the macroscopic landscape of this inner city, starting with its most prominent feature, the cerebral cortex. Picture it, if you will, as the crumpled, convoluted surface of a magnificent ancient map, spanning across the top and sides of our brain. This thin outer layer, only a few millimeters thick, is the crown jewel of our nervous system, responsible for our highest cognitive functions, our perception, our language, our memory, our abstract thought, our consciousness itself. It is here that the silent symphony truly finds its grandest stage, where the individual notes of neuronal activity are orchestrated into complex melodies of thought and experience. The cerebral cortex isn't a monolithic entity. Rather, it is beautifully divided into 4 major lobes, each with its own primary responsibilities, yet constantly collaborating with the others. We might think of them as specialized departments within our grand inner university, each focusing on a distinct area of study, but all contributing to the overarching pursuit of knowledge and understanding. Let us begin our exploration with the frontal L lobe, situated at the very front of your brain, just behind your forehead. This is in many ways the conductor of our internal orchestra, the executive suite of our consciousness. The frontal lobe is where we find our capacity for planning, decision-making, problem-solving, and exercising judgment. It's the region that allows you to envision the future, to set goals, and to inhibit impulsive behaviors. This is where your unique personality largely resides, where your moral compass is calibrated, and where you orchestrate complex social interactions. Imagine trying to plan a trip or decide what to cook for dinner, or even just hold a coherent conversation. These are all intricate dances choreographed by your frontal lobe. It's also home to the wet motor cortex, a strip of tissue running across the back of the frontal lobe which is responsible for initiating and controlling all your voluntary movements, from the subtle flick of an eyelid to the grand gesture of an artist's brushstroke. When you reach for a cup of tea, it is your frontal lobe that sends the precise commands down to your muscles, translating intention into action. Without this remarkable region, our lives would lack direction, purpose, and the very essence of our individual will. Moving behind the frontal lobe, we encounter the parietal lobe, nestled between the frontal and occipital lobes. This region might be considered the brain's grand sensory integration center, the master cartographer of our spatial awareness. The parietal lobe takes in information from our senses, touch, temperature, pain, pressure, and processes it, allowing us to understand our body's position in space and its relationship to the world around us. It helps us navigate to understand where objects are relative to us, and to perform tasks that require spatial reasoning, such as dressing ourselves or understanding a map. When you reach out to touch a smooth stone or feel the warmth of the sun on your skin, it is your parietal lobe that interprets these sensations, not just as raw data, but as meaningful experiences. It integrates sensory input from various parts of the body, creating a coherent three-dimensional map of our physical self and our surroundings. It allows us to distinguish between the textures of velvet and sandpaper, to know instinctively where our hand is in relation to our face, even with our eyes closed. This lobe weaves together the tactile world with our internal body schema, grounding us in our physical reality. Next, let us descend to the sides of the brain, just beneath the parietal and frontal lobes, where we find the temporal lobe. This region is a vital hub for auditory processing, memory formation, and language comprehension. Think of it as the brain's intricate listening post and its vast, ever-expanding library. The temporal lobe processes sounds, transforming vibrations in the air into meaningful words, music and environmental cues. It's where the rich tapestry of speech is decoded, allowing us to understand the nuances of spoken language. Within the temporal lobe, we find structures crucial for memory, most notably the hippocampus, which acts like a diligent librarian, organizing and consolidating new experiences into long-term memories. It's the reason you can recall what you had for breakfast this morning, or remember the name of a new acquaintance. Another key area here is Wernicke's area. Essential for language comprehension, it's what allows you to understand the words I'm speaking right now, weaving them into a coherent narrative. The temporal lobe also plays a significant role in object recognition and facial recognition, helping us identify the people and things that populate our world. Without its intricate workings, our world would be a cacophony of meaningless sounds and an endless stream of unfamiliar faces. Finally, at the very back of the brain, we encounter the occipital lobe. This is the brain's dedicated visual processing center, the canvas upon which our inner eye paints the world. Every image you see, every color, every shape, every movement is meticulously processed here. When light hits your retina, the signals travel to the occipital lobe, where they are transformed into the vivid, detailed visual experience we perceive. It's not just about seeing, it's about interpreting what we see, recognizing patterns and understanding spatial relationships within our visual field. Imagine the breathtaking complexity involved in distinguishing a friend's face from a stranger's, or navigating a crowded street, or appreciating the subtle hues of a sunset. All of this intricate visual computation is orchestrated by the occipital lobe, turning raw light data into the rich, meaningful visual world that guides our every step and enriches our every moment. While these four cortical lobes form the magnificent surface of our brain, they are not alone in their work. Beneath this convoluted cortex lies a fascinating array of subcortical structures, vital for processing, relaying, and integrating information, acting as essential partners in the brain's grand design. Consider the thalamus, often referred to as the brain's central relay station. Almost all sensory information, sight, sound, touch, taste, passes through the thalamus before being routed to the appropriate areas of the cerebral cortex for further processing. It acts like a sophisticated switchboard operator, directing incoming calls to the correct department, ensuring that information reaches its intended destination efficiently and effectively. Just below the thalamus, we find the diminutive yet immensely powerful hypothalamus. This tiny structure, no larger than an almond, is a master regulator of our body's internal environment, maintaining homeostasis. It controls our basic drives, hunger, thirst, sleep, body temperature, and even our emotional responses. It's the brain's internal thermostat and clock, quietly ensuring that our fundamental physiological needs are met, underpinning our very survival. Deep within the temporal lobe and extending into other regions lies the limbic system, often called the emotional brain. This ancient and powerful system is a constellation of structures, including the aforementioned hippocampus for memory and the amygdala, a small almond-shaped cluster of neurons that is crucial for processing emotions, particularly fear and pleasure. The amygdala acts as our internal alarm system, quickly assessing threats and triggering our fight or flight response, while also playing a role in the formation of emotional memories. This system imbues our experiences with feeling, connecting our thoughts to our deepest emotional currents. And then there are the basal ganglia, a group of interconnected nuclei located deep within the cerebral hemispheres. These structures are vital for the control of voluntary movement, the learning of habits, and the smooth execution of motor sequences. They act like a sophisticated filter, refining our movements, ensuring grace and precision, and playing a critical role in automating learned behaviors, from riding a bicycle to playing a musical instrument. As we survey this incredible landscape, from the intricate cellular dance of neurons to the specialized architecture of lobes and subcortical structures, a profound truth emerges. No single region of the brain works in isolation. The brain is a symphony, not a series of solos. Every thought, every feeling, every perception, every memory is the result of a vast interconnected network of activity spanning multiple regions, communicating through an exquisitely synchronized exchange of electrical impulses and chemical signals. The frontal lobe doesn't just plan, it collaborates with the temporal lobe for language, the parietal lobe for spatial awareness, and the limbic system for emotional context. The visual information processed by the occipital lobe isn't just seen, it's integrated with memories stored in the temporal lobe, emotional significance from the amygdala, and spatial context from the parietal lobe, all orchestrated by the executive functions of the frontal lobe. This constant dynamic communication, this ceaseless integration of information, is what creates the rich, seamless, and unified experience of being you. This, my friends, brings us back to the heart of the mystery, the grandest question of all. How does this tight symphony of chemical-electrical exchanges, this intricate dance of specialized yet interconnected parts, give rise to the subjective experience of consciousness, of a self that perceives, feels, and understands? We have peeled back layers, revealing the astonishing complexity of the brain's structure and function, yet the leap from neural activity to subjective awareness remains the most profound frontier of neuroscience. We are truly just beginning to appreciate the depth of this inner cosmos, to understand how billions of tiny, elegant trees, whispering chemicals across microscopic gaps, can collectively conjure the entirety of our human experience. As we conclude this chapter, I invite you to carry this sense of wonder with you. In our next session, we will delve deeper into how these networks and regions create specific functions, exploring the captivating processes of perception, memory, and perhaps even daring to touch upon the elusive nature of consciousness itself. For now, let us rest in the quiet contemplation of this magnificent organ, this universe within, marveling at its complexity, its elegance, and its enduring mystery. Until then, may your dreams be filled with the silent music of your own incredible mind. We've journeyed deep into the intricate landscape of the brain, exploring its fundamental building blocks and the grand architecture that houses our very essence. We've witnessed the silent ballet of electrical impulses and chemical whispers, the precise dance of neurotransmitters, and the specialized roles of each cortical lobe and subcortical structure. Yet as we stand at the threshold of this understanding, a profound question echoes in the quiet chambers of our minds. How does this magnificent, interconnected machine not only function, but learn, remember, and ultimately become us? How does the fleeting present solidify into the enduring past, shaping the continuous narrative we call self? Tonight, my friends, we turn our gaze to the dynamic processes that breathe life into this neural canvas, the miraculous capacities of learning and memory. These aren't merely functions, they are the very threads that weave the tapestry of our personal histories, allowing us to adapt, to grow, and to imbue our existence with meaning. Without the ability to learn and remember, each moment would be an isolated island, an experience without context, a life without continuity. Imagine, if you will, that the brain is not just a static map, but a living, breathing library, constantly writing, rewriting, and cross-referencing its vast collection of stories. Every sensation, every thought, every emotion leaves an imprint, subtly altering the very structure of this library. This incredible adaptability, this capacity for change, is what we call neural plasticity, a concept we briefly touched upon, but one that truly underpins the magic of learning and memory. Let us begin with memory itself. What is it truly? It is not a single entity nor a singular location in the brain. Rather, memory is a constellation of systems, each designed to capture, store, and retrieve different facets of our experience. Think of it as a river with many tributaries, each flowing with different kinds of information, eventually converging or diverging to form the vast ocean of our personal history. We can broadly categorize memory into several forms. At the most immediate level, we have sensory memory, a fleeting echo of the world around us. When you glance at a scene and then close your eyes, that momentary after-image, that brief auditory reverberation, is sensory memory at work. It lasts mere milliseconds to a few seconds, a raw, unfiltered snapshot of sensory input, most of which fades before it can even be consciously processed. It's like a quick sketch before the artist decides what details to commit to canvas. From this torrent of sensory information, a select few details are plucked and brought into our short-term memory, often synonymous with working memory. This is your mental workbench, where you actively hold and manipulate information for a brief period, perhaps remembering a phone number just long enough to dial it, or following the steps of a recipe as you cook. Its capacity is surprisingly limited, typically holding only about 7 pieces of information at a time, and it lasts for about 20 or 30 seconds, unless actively rehearsed. Working memory is crucial for planning, problem-solving, and decision-making. It's the conscious now of our mental processing. But the true marvel, the vast repository of our lives, is long-term memory. This is where experiences, facts, skills, and emotions reside, potentially for a lifetime. Long-term memory is often further divided into 2 major types: explicit or declarative memory and implicit or non-declarative memory. Explicit memory is what we consciously recall and can verbalize. It's the memory of facts and events. Semantic memory is our knowledge of the world, facts, concepts, language, the capital of France, the laws of physics. It's the encyclopedia within our minds, devoid of personal context. Episodic memory, on the other hand, is the memory of specific events, experiences, and their personal context. What you had for breakfast your first day of school, the joy of a particular sunset. It's your personal autobiography, rich with sensory details and emotional resonance. It allows us to mentally time travel to re-experience moments from our past. Then there is implicit memory, the memory that operates beneath the surface of conscious awareness. We demonstrate it through our actions, our habits, our conditioned responses, without necessarily being able to articulate how we know or do something. Procedural memory is perhaps the most familiar form of implicit memory. It's the memory for skills and habits, riding a bicycle, tying your shoelaces, playing a musical instrument. You don't consciously recall the steps, your body simply knows how. It's a beautiful testament to the brain's ability to automate complex sequences of actions. Other forms of implicit memory include priming, where exposure to one stimulus influences the response to a subsequent stimulus. Seeing the word doctor makes you recognize nurse faster. And classical conditioning, where an association is formed between two stimuli, like Pavlov's dog salivating at the sound of a bell. Now, how does this intricate system of memory actually work at the cellular level? This brings us back to the heart of neural plasticity, the prevailing scientific understanding often summarized by the adage, "Neurons that fire together wire together," comes from the brilliant Donald Hebb. He proposed that when two neurons are repeatedly activated at the same time, the connection or synapse between them becomes stronger. This strengthening is the physical manifestation of learning, the cellular footprint of a memory being formed. This synaptic strengthening is elegantly explained by a phenomenon called long-term potentiation, LTP. Imagine a delicate conversation between two neurons across a synapse. With LTP, repeated synchronized communication makes that conversation easier, louder, and more efficient. The presynaptic neuron becomes better at releasing neurotransmitters, and the postsynaptic neuron becomes more sensitive to receiving them, perhaps by increasing the number of receptors on its surface. It's like paving a frequently used path in a garden, making it smoother and faster to traverse. This enduring enhancement of synaptic transmission is considered a primary cellular mechanism for learning and memory storage. Conversely, the brain also employs long-term depression, LTD, a mechanism that weakens synaptic connections. This is just as crucial as strengthening them. Why? Because learning isn't just about acquiring new information. It's also about forgetting irrelevant details, refining existing knowledge, and pruning away unnecessary connections to maintain efficiency and flexibility. If LTP is paving a path, LTD is letting an unused path grow over, allowing resources to be allocated elsewhere. Together, LTP and LTD provide the dynamic toolkit for the brain to continuously sculpt its neural networks based on experience. So where does all this happen? While memory is distributed across many brain regions, certain areas play particularly crucial roles. The hippocampus, part of the limbic system we discussed, is absolutely vital for the formation of new explicit memories, especially episodic ones. It acts as a kind of temporary holding zone, processing and consolidating new information before it is sent to other cortical areas for long-term storage. Think of it as the librarian who diligently sorts new books, assigns them categories, and prepares them for their permanent shelves throughout the library. Damage to the hippocampus can leave individuals unable to form new memories, living in a perpetual present, even while old memories remain largely intact. The prefrontal cortex, residing in our frontal lobe, is deeply involved in working memory, strategic retrieval of memories, and linking memories to their emotional context. It's the executive editor, deciding what information is relevant, how to access it, and how to integrate it into our current understanding. The amygdala, another limbic structure, imbues memories with emotional significance, particularly fear and pleasure, explaining why emotionally charged events are often so vividly remembered. And the poor cerebellum, that elegant structure at the back of the brain, is a key player in procedural learning and motor skill memory. Each region contributes its unique expertise to the grand symphony of memory. The process of memory formation involves several stages. 1. Encoding. The initial processing of information, transforming sensory input into a form that can be stored in the brain. This can be shallow, e.g., just the sound of a word, or deep, e.g., understanding the word's meaning and relating it to personal experience. 2. Storage. The retentions of encoded information over time. This is where the synaptic changes of LTP and LTD come into play, physically altering neural networks. 3. Consolidation. The process by which unstable, newly formed memories are gradually stabilized and transferred from temporary storage, like the hippocampus, to more permanent storage sites in the cerebral cortex. This often happens during sleep, a time when the brain replays and strengthens recent experiences. 4. Retrieval, the act of accessing stored information. This isn't a perfect playback. Retrieval is often a reconstructive process, where bits and pieces of information are reassembled, sometimes influenced by our current mood, beliefs, or even new information. And this brings us to a fascinating yet often overlooked aspect of memory, its fallibility. Our memories are not like perfect video recordings. They are dynamic, malleable, and subject to distortion, suggestion, and forgetting. Each time we retrieve a memory, we subtly alter it, making it susceptible to change. This reconstructive nature of memory, while sometimes leading to inaccuracies, also highlights its adaptive brilliance. It allows us to update our understanding of the past in light of new experiences, integrating new information into our personal narrative. It's not about perfect fidelity, but about maintaining a coherent, useful story of who we are and how we navigate the world. So as we reflect on learning and memory, we begin to grasp the incredible dynamism of the brain. It is not a fixed machine, but an ever-evolving narrative, constantly shaped by every interaction, every thought, every emotion. The billions of neurons once seen as mere electrical components are revealed as tireless scribes, ceaselessly documenting and revising the story of our lives. And here, my friends, we circle back to our profound mystery. How does this continuous stream of encoding, storing, and retrieving information give rise to our unique sense of self? How do these physical changes in synaptic strength translate into the subjective experience of remembering a cherished moment or learning a new skill? It is in this constant flux, this beautiful ballet of creation and recreation, that our consciousness finds its footing, building a coherent identity out of an endless stream of sensory input and internal reflection. The brain, in its capacity to learn and remember, is not merely processing data, it is crafting a unique world for each of us, a deeply personal universe of meaning and experience. It is the architect of our past, the foundation of our present, and the compass guiding our future. As we continue our exploration, let us carry this profound appreciation for the brain's dynamic nature, understanding that every moment shapes the symphony of self, a symphony that is always still being written. The journey continues, and with each step the wonder only deepens. As we journey deeper into the intricate landscape of our own minds, we've explored the very foundations, the neurons, the neurotransmitters, the grand architecture of the brain, and the delicate art of learning and memory. We've seen how our experiences are encoded, stored, and retrieved, shaping the tapestry of who we are, moment by fleeting moment. Yet, if memory sculpts the form of our being, what breathes life into that sculpture? What gives it colour, urgency, and direction? Tonight, dear friends, we turn our gaze to the vibrant, often tumultuous, world of motions and motivation. These are not mere afterthoughts in the grand design of the brain. They are the very currents that drive us, the silent orchestrators of our decisions, and the profound wellsprings of our humanity. Without them, memory would be a cold, factual archive, and learning an uninspired task. With them, life becomes a rich, deeply felt experience full of purpose and meaning. Imagine for a moment a world stripped of feeling. A memory of a sunset would be just data, wavelengths of light, angles of incidents. A memory of a loved one, merely a collection of features and shared events. But we know it is so much more, don't we? It is the warmth in our chest, the ache of longing, the rush of joy. These are the emotions, complex physiological and cognitive responses that colour our existence, guiding us, warning us, and connecting us to the world and to each other. At the heart of our emotional landscape lies a network of structures, many of which we've touched upon before, but which now demand our focused attention. Primarily, we return to the limbic system, that ancient, deeply rooted part of our brain, often referred to as our emotional brain. Within this system, the amygdala stands out, a pair of almond-shaped nuclei nestled deep within the temporal lobes. Think of the amygdala as the brain's vigilant sentinel, its rapid response alarm system. It is exquisitely tuned to detect threats, to process fear, and to imprint emotional significance onto our memories. When you feel that sudden jolt of fear, that primal surge of adrenaline, it is often your amygdala sounding the alert, long before your conscious mind can fully process the danger. It tells us, in no uncertain terms, pay attention, this matters. And while the hippocampus, as we discussed, is crucial for forming new explicit memories, it also plays a vital role in emotion, particularly in providing the context for those emotional memories. It helps us remember where and when an emotionally charged event occurred, weaving the feeling into the fabric of our personal narrative. The amygdala provides the intensity of the emotion, while the hippocampus provides the story. But our emotional experience is far more nuanced than just fear and memory. Consider the insula, a fascinating region tucked deep within the folds of the cerebral cortex. The insula is our window into our internal bodily states, our interoception. It helps us feel the growl of hunger, the racing of a heart, the warmth of a blush, or the chilling grip of disgust. It is where our subjective visceral feelings are born, transforming raw physiological sensations into conscious emotional experience. When you say you feel it in your gut, you are in a very real sense experiencing the work of your insula. It connects the physical sensations of your body to the emotional meaning you ascribe to them. Then there is the prefrontal cortex, PFC. Particularly its ventromedial and orbitofrontal regions. While the limbic system might be the passionate heart of emotion, the PFC is its wise, albeit sometimes overwhelmed regulator. It's where emotional signals are integrated with rational thought, where we learn to modulate our impulses, and where we make decisions that are not solely driven by raw feeling, but by a consideration of consequences and social norms. The PFC allows us to pause, to reflect, to choose how we respond to an emotion rather than simply reacting. It's the negotiator between our primal urges and our higher ideals, the conductor attempting to bring harmony to the emotional symphony. This intricate dance between the impulsive limbic system and the contemplative PFC is fundamental to our emotional intelligence and our ability to navigate the complexities of social life. And let us not forget the anterior cingulate cortex, ACC. Another key player. Located just above the corpus callosum, the ACC is involved in detecting conflicts, monitoring errors, and processing both physical and emotional pain. It's the part of your brain that lights up when you make a mistake or when you feel the sting of social rejection. It contributes to our awareness of our own emotional state and helps us to adjust our behavior accordingly. As with all things in the brain, these regions do not operate in isolation. They form a dynamic, interconnected network, a beautiful ballet of electrical impulses and chemical messengers. And speaking of chemical messengers, the very neurotransmitters we discussed in Chapter 2 return now as central characters in our emotional drama. Dopamine. That elusive molecule of reward and motivation fuels our pursuit of pleasure and our drive for achievement. Serotonin, the gentle modulator, influences our mood, our sense of well-being, and our overall emotional stability. Norepinephrine, the alertness chemical, prepares us for action, sharpening our focus in times of stress or excitement. Beyond these familiar players, a few others deserve special mention in the realm of emotion. Consider oxytocin, often dubbed the love hormone or cuddle chemical. This remarkable neuropeptide plays a crucial role in social bonding, trust, empathy, and maternal behavior. It fosters feelings of connection and attachment, underpinning the warmth of friendship and the profound bond between parent and child. And then there are the stress hormones like cortisol, released by the adrenal glands under the command of the hypothalamus. Cortisol prepares our bodies for the fight or flight response, mobilizing energy and heightening our senses, a powerful, albeit taxing aspect of our emotional survival mechanism. Now, if emotions are the colors and textures of our inner world, then motivation is the engine, the driving force that propels us forward. Motivation is the why behind our actions, the persistent whisper or insistent roar that guides our choices, big and small. It's what makes us seek food when hungry, learn a new skill, pursue a passion, or connect with others. At the core of much of our motivated behavior lies the brain's reward system, a powerful network primarily driven by dopamine. This mesolimbic pathway, originating in the whole ventral tegmental area, VTA, and projecting to the nucleus accumbens and parts of the prefrontal cortex, is not simply about pleasure itself, but more profoundly about anticipation and pursuit. It's the system that tells us, this is important, go get it. When you achieve a goal, experience something novel, or engage in a behavior vital for survival like eating or social connection, this system is activated, releasing dopamine and reinforcing that behavior. It's a powerful learning mechanism, teaching us what to seek out and what to avoid. It's what drives us to learn, to grow, to innovate, and yes, sometimes to fall into patterns of addiction when the system is hijacked by artificial rewards. Motivation can arise from within us as intrinsic motivation, the joy of learning for its own sake, the satisfaction of mastering a craft, the simple pleasure of helping another. Or it can be spurred by external factors as extrinsic motivation, the desire for a reward, the avoidance of punishment, the pursuit of recognition. both play crucial roles in shaping our daily lives and long-term aspirations. Furthermore, basic biological drives like hunger, thirst, and the need for sleep are powerful motivators rooted in our need for homeostasis, the body's constant effort to maintain internal balance. The hypothalamus, that small but mighty structure we discussed earlier, is the master regulator here, sensing imbalances and orchestrating the physiological and behavioral responses needed to restore equilibrium. When your body needs water, the hypothalamus sends signals that create the sensation of thirst, motivating you to seek a drink. It becomes clear, doesn't it, how intimately intertwined emotions and motivation are? Emotions often fuel our motivation. The joy of success motivates us to strive for more. The fear of failure motivates us to prepare diligently. The love for our family motivates us to protect and provide. Conversely, motivated behaviors can generate emotions. Achieving a long-sought goal brings elation. Failing despite our best efforts can bring disappointment or frustration. They are two sides of the same coin, constantly influencing and shaping each other in a beautiful, complex dance. As we reflect on these incredible systems, we are once again confronted with the profound mystery that lies at the heart of neuroscience. We can map the neural circuits, identify the chemical messengers, and observe the physiological responses. We can describe how the amygdala fires, how dopamine surges, how the insula registers a gut feeling. But how do these physical events coalesce into the subjective lived experience of feeling joy, of burning with ambition, of being moved to tears by a piece of music? How does the silent symphony of our brain's activity give rise to the rich, vibrant tapestry of our emotional lives and our conscious will to act? This, my friends, remains one of the most compelling and enduring questions. It is the bridge between the physical and the phenomenal, between the matter of the brain and the marvel of the mind. As we continue to unravel these mysteries, we gain not only scientific understanding but also a deeper appreciation for the intricate, awe-inspiring complexity of what it means to be human. The journey continues, always inviting us to look closer, to wonder more, and to marvel at the universe within. Welcome back, dear friends, to the quiet embrace of Dreamy Academy. As the twilight deepens around us, we continue our journey inward, a journey that has so far unveiled the intricate dances of neurons, the rich tapestry of neurotransmitters, the grand architecture of the brain, and the profound mechanisms behind our memories, emotions, and motivations. We've seen the brain as a magnificent orchestra, each section playing its part, each instrument contributing to a complex, beautiful score. But tonight, we turn our gaze towards the conductor, the audience, and indeed, the very experience of the music itself. For all the incredible mechanics we've explored, all the chemical whispers and electrical impulses, there remains a question that sits at the very heart of our existence. How do these physical processes give rise to the subjective, vibrant, and utterly unique experience of being? How do they coalesce into consciousness, attention, perception, and that most intimate of mysteries, our very sense of self? Imagine for a moment that you are standing at the edge of a vast, star-dusted ocean. We've catalogued the currents, measured the tides, understood the chemistry of the water, and even observed the life teeming within its depths. But now we ask, what is it like to feel the spray on your face, to hear the roar of the waves, to see the endless horizon? This is the realm of consciousness, a concept so elusive, yet so undeniably present. What is consciousness? It is, in its simplest form, the state of being aware of one's own existence and surroundings. It's the light turning on in the theatre of your mind illuminating the stage of your inner world. It's not a single switch, nor a specific region of the brain that we can point to and declare, "Here it is." Instead, we understand consciousness as an emergent property, a grand symphony arising from the synchronized activity of countless neural networks across the entire brain. It is the integrated product of all the processes we've discussed: sensory input, memory retrieval, emotional coloring, motivational drives, all woven together into a coherent, flowing narrative. Think of it like this. A single note played on a piano is just a sound. Many notes played together in harmony and rhythm become a melody. And that melody, intertwined with other melodies from different instruments, becomes a symphony that can stir the soul. Consciousness is that symphony, constantly unfolding, constantly evolving. But how does the brain manage to craft this unified experience from the cacophony of incoming data? This brings us to the crucial role of attention. Our senses are constantly bombarded with an overwhelming flood of information. The hum of the refrigerator, the distant chirping of crickets, the texture of the fabric against your skin, the subtle scent in the air, the myriad thoughts swirling in your mind. If we were consciously aware of everything at once, it would be sheer chaos. So the brain acts as a masterful editor, a discerning spotlight operator. Attention is this spotlight, illuminating what is relevant and allowing the rest to recede into the shadows. We have different kinds of attention, each serving a vital purpose. There's selective attention, which allows you to focus on a single voice in a crowded room, or to concentrate on these words despite other distractions. This is often guided by our goals and interests, heavily involving areas like the prefrontal cortex and the parietal lobe, which help us orient ourselves in space and process sensory information. Then there's sustained attention, the ability to maintain focus over a longer period, like when you're deeply engrossed in a book or a complex task. And there's divided attention, the tricky art of multitasking, though our brains are often simply switching rapidly between tasks rather than truly doing them simultaneously. Imagine your brain as a bustling city at night. Millions of lights are on, representing neural activity. Attention is the focused beam of a searchlight highlighting specific buildings or streets, allowing you to perceive their details while the rest of the city glows in a softer, less defined way. Without attention, consciousness would be a blurry, overwhelming mess. It is the gatekeeper, deciding what gets to enter the stage of our awareness. Hand in hand with attention is perception. While sensation is the raw input, the light hitting your retina, the sound waves vibrating your eardrum, perception is the brain's interpretation and organization of that raw data into meaningful experiences. It's the process by which those flashes of light become the image of a friend's smiling face, or those vibrations become the melody of a beloved song. Our perception is not merely a passive reception of reality, it is an active construction. The brain doesn't just record the world, it creates it based on sensory input, yes, but also on our memories, expectations, emotions, and past experiences. This is why two people can witness the same event and perceive it differently, or why an optical illusion can trick our minds. Our brains are constantly making educated guesses, filling in gaps, and building a coherent narrative from fragmented cues. Think of it like an artist working on a canvas. The raw pigments are the sensations. The artist's skill, knowledge of color theory, personal style, and emotional state all contribute to how those pigments are applied and interpreted, resulting in a unique painting, the perception. The visual cortex, temporal lobe for auditory processing, and parietal lobe for integrating spatial information all play crucial roles. But it is the dynamic interplay across these regions, constantly cross-referencing and refining, that gives rise to our rich, perceptual world. And then we arrive at perhaps the most profound of all the brain's creations, the soul, sense of self. Who are you in the deepest, most fundamental sense? Is it your memories, your personality traits, your physical body, your dreams and aspirations? It is in essence all of these, and yet so much more. The sense of self is not localized to a single self-center in the brain. Instead, it emerges from the continuous integration of myriad processes: your autobiographical memories, from the hippocampus and prefrontal cortex, your emotional landscape shaped by the limbic system, your bodily sensations processed by the insular and somatosensory cortex, your intentions and plans orchestrated by the prefrontal cortex, and your ongoing perception of the world around you. It's as if the brain is constantly compiling a living, breathing biography of you. This biography is updated moment by moment, incorporating new experiences, reflecting on past ones, and anticipating future ones. This internal narrative, this continuous thread of identity, is what allows you to feel like the same person who woke up this morning, who experienced yesterday, and who dreams of tomorrow. A network of brain regions, often referred to as the default mode network, DMN, becomes particularly active when we are not focused on an external task, when our minds are wandering, reminiscing, or imagining. This network is thought to be deeply involved in self-referential thought, introspection, and constructing our internal narrative, a testament to the brain's tireless work in maintaining our sense of who we are, even when we're simply letting our minds drift. The sense of self is also profoundly social. Our identities are shaped by our interactions with others, by the roles we play, and by how we perceive ourselves in relation to the social world. The mirror neuron system, which allows us to understand and empathize with the actions and intentions of others, plays a subtle but significant role in how we construct and refine our own sense of self. We are, in a very real way, reflections of our experiences and connections. So as we bring our exploration tonight to a gentle close, we are left with a deeper appreciation for the brain's most miraculous feat. From the silent symphony of individual neurons to the grand orchestration of attention, perception, and consciousness, the brain tirelessly works to create you. It crafts your subjective reality, filters your experiences, and weaves together the intricate threads of memory, emotion, and motivation into the unique tapestry of yourself. We have traversed the vast landscapes of the brain, from its microscopic components to its grand, emergent properties. And while we have illuminated many pathways and revealed countless wonders, the fundamental mystery of how mere matter gives rise to mind, how electrical impulses become the feeling of joy or the color red, how a collection of cells generates a unified sense of I, this mystery remains, shimmering at the very edge of our understanding. Perhaps it is this enduring mystery, this final frontier within ourselves, that makes the study of the brain so endlessly compelling, so profoundly beautiful. It reminds us that even with all our knowledge, there is always more to discover, more to wonder at, within the silent living universe that resides between our ears. Thank you for sharing this contemplative journey with me tonight. May your own inner universe continue to inspire awe and curiosity. Until next time, from all of us at Dreamy Academy, good night. As we stand at the precipice of understanding the brain, having charted its intricate landscapes of neurons, networks, and the very foundations of consciousness, we inevitably arrive at a profound yet often challenging dimension of our exploration. We've marvelled at how the brain weaves together sensation, emotion, memory and thought into the tapestry of our subjective experience, giving rise to that inexplicable feeling of I. But what happens, dear friends, when this delicate symphony falters, when the intricate dance of chemistry and electricity goes awry? This brings us to a crucial and deeply human aspect of neuroscience, the study of brain disorders and mental health. It is here that the abstract beauty of neural circuits confronts the lived reality of suffering, offering us not only a deeper understanding of pathology, but also a more profound appreciation for the brain's incredible, often fragile balance. Imagine, if you will, the brain as a meticulously crafted clock, each gear, spring and a lever working in perfect harmony to tell time. For most of our journey, we've been admiring the clock's flawless operation. Now, we turn our gaze to moments when a gear slips, a spring loses its tension, or a lever misfires, altering the very rhythm of existence for the person whose internal clock it is. Mental health conditions and neurological disorders are not simply faults in the system. They are complex manifestations of alterations in brain structure, function, and chemistry, often influenced by an intricate interplay of genetic predispositions, environmental factors, and life experiences. They remind us that our subjective reality, our emotions, our thoughts, and our sense of self are inextricably linked to the physical state of our brain. Let us begin by considering the very building blocks we've discussed, those chemical whispers, the neurotransmitters. We know that dopamine fuels our motivation and reward, serotonin modulates our mood, and GABA calms the neural storm. Picture what might happen if these chemical messengers are produced in excess or scarcity, if their receptors become oversensitive or unresponsive, or if the delicate balance of excitatory and inhibitory signals shifts. Take, for instance, mood disorders, such as major depressive disorder or bipolar disorder. In depression, we often see a reduction in the activity of certain neurotransmitter systems, serotonin, norepinephrine and dopamine, creating a pervasive sense of sadness, anhedonia, inability to feel pleasure, and a profound alteration in thought patterns. The brain's reward circuits may become less responsive. The prefrontal cortex, responsible for executive function and emotional regulation, might show altered activity, and the amygdala, often hyperactive in fear responses, might contribute to feelings of hopelessness. For someone experiencing depression, the world literally looks, feels, and is different. Their internal landscape is shrouded, and the very colours of life seem muted. In contrast, bipolar disorder presents a dramatic swing between depressive states and periods of intense mania, characterized by elevated mood, racing thoughts, increased energy, and sometimes impulsive behavior. Here, the brain's regulatory mechanisms seem to struggle with maintaining equilibrium, with complex shifts in neurotransmitter activity and connectivity across multiple brain regions, including those involved in emotion, reward, and cognition. It's as if the internal thermostat for mood is wildly fluctuating, unable to settle into a stable range. Then we encounter the realm of anxiety disorders, where the brain's natural alarm system, vital for survival, becomes overactive and dysregulated. In conditions like generalized anxiety disorder or panic disorder, the amygdala, our ancient fear center, might be in a constant state of heightened alert, perceiving threat where none exists. The prefrontal cortex, which normally helps to temper these emotional responses, may struggle to exert its calming influence. Neurotransmitters like norepinephrine, involved in the fight or flight response, can surge, leading to the physical sensations of anxiety, a racing heart, shortness of breath, a knot in the stomach. For someone with an anxiety disorder, the world can feel perpetually threatening, a place of unseen dangers, and their subjective experience is dominated by a relentless sense of unease. Consider also the profound impact of neurodevelopmental disorders, conditions that arise from atypical brain development. In autism spectrum disorder, ASD, for example, we see differences in how neural networks are formed and how different brain regions communicate. This can affect social cognition, communication, and lead to repetitive behaviors. The social brain, regions involved in understanding others' intentions and emotions, like the fusiform face area or the superior temporal sulcus, may process information differently. This isn't a choice, it's a fundamental difference in how the brain is wired, leading to a unique way of perceiving and interacting with the world. A different kind of subjective experience, often rich and detailed in its own ways, yet challenging in navigating social norms. Or think of attention deficit hyperactivity disorder, ADHD, where difficulties in executive functions, planning, focus, inhibitory control are prominent. Here, the prefrontal cortex, along with circuits involving dopamine and norepinephrine, often shows differences in activity and connectivity. The brain's ability to filter distractions and sustain attention might be less efficient, leading to a subjective experience of constant internal noise or an inability to stick to a single task. Beyond these, we also encounter neurodegenerative disorders, conditions that involve the progressive loss of neurons and the brain function over time. In Alzheimer's disease, for instance, we witness the insidious accumulation of abnormal proteins, amyloid plaques and tau tangles, that disrupt neuronal communication and eventually lead to cell death, particularly in areas crucial for memory, like the hippocampus and cortex. The gradual erosion of memory, cognition, and eventually personality is a heartbreaking testament to how our sense of self is intertwined with the integrity of our neural architecture. The very thread of one's narrative built upon episodic memories begins to fray, profoundly altering the subjective experience of who one is. Similarly, Parkinson's disease is characterized by the degeneration of dopamine-producing neurons in the substantia nigra, a region vital for smooth, coordinated movement. The resulting tremors, rigidity, and bradykinesia, slowed movement, are stark reminders of the brain's control over our physical presence in the world. But beyond motor symptoms, Parkinson's also often involves cognitive and mood changes, illustrating the widespread impact of neurotransmitter imbalances. What is critical to understand, my friends, is that these conditions are rarely attributable to a single cause. They are multifactorial, emerging from a complex interplay of genetics, epigenetics, how genes are expressed, early life experiences, trauma, chronic stress, inflammation, and even gut microbiome health. Neuroscience is constantly unraveling these layers, moving beyond simplistic explanations to embrace the intricate web of causation. And this brings us back to that profound mystery of consciousness and the sense of self. When the brain is affected by a disorder, it's not just a collection of symptoms, it's a fundamental shift in how an individual experiences reality. How does depression alter the feeling of joy? How does anxiety reshape the perception of safety? How does a neurodegenerative disease erode the essence of who one has always been? These are not merely scientific questions, they are deeply philosophical inquiries into the nature of existence itself. Our journey through these challenging landscapes of the brain fosters not just knowledge, but also a profound sense of empathy. By understanding the biological underpinnings of mental health conditions and neurological disorders, we dismantle the walls of stigma and judgment. We move away from viewing these as character flaws or personal failings and towards recognizing them as legitimate health conditions, as real and impactful as any physical ailment. The brain, our most complex organ, is just as susceptible to illness and dysfunction as the heart or the lungs. The beauty of neuroscience, even in these difficult explorations, lies in its relentless pursuit of understanding, its dedication to shedding light into the darkest corners of human experience. With every new discovery, every refined treatment, every deeper insight into neural pathways, we move closer to alleviating suffering and restoring balance. We learn more about the brain's remarkable capacity for resilience, for adaptation, for finding new ways to cope and even thrive amidst adversity. So as we contemplate these challenges, let us carry forward not despair, but a renewed sense of purpose and wonder. The brain, in its moments of struggle, teaches us as much about its incredible design as it does in its moments of grace. It reminds us of the delicate dance of life within us, and the enduring quest to nurture and understand that most precious of instruments, the human mind. Our exploration continues, ever seeking to comprehend the silent symphony that defines us all, in all its varied and complex expressions. Welcome back, dear friends, to Dreamy Academy. As the starlight filters through our metaphorical window, casting long, gentle shadows, we find ourselves on the cusp of an extraordinary new chapter. In our last gathering, we journeyed into the intricate landscape of brain disorders and mental health, witnessing the profound fragility and resilience of this inner universe. We grappled with how alterations, subtle or stark, can reshape perception, emotion, and indeed the very fabric of oneself. It was a poignant exploration, reminding us of the immense responsibility we bear in understanding and caring for this most vital organ. Tonight, we turn our gaze from understanding the brain's natural states and its vulnerabilities to a frontier that once belonged solely to science fiction, the direct interface. We are stepping into the dawn of neurotechnology, a realm where the human mind and external machines begin to converse, not through the traditional senses, but through a language of electrical impulses and digital translation. Imagine, if you will, a bridge, not one of stone or steel spanning a river, but an invisible, intricate pathway connecting the universe within your skull to the vast, expanding world of technology. This is the essence of a brain-computer interface, or BCI, a direct communication link between a wired brain and an external device. For centuries, our interaction with the world has been mediated by our senses and our motor systems. We see, we hear, we touch, and we move. But what if we could bypass these traditional conduits? What if thought itself could become an action, directly commanding a machine? It sounds like a dream, doesn't it? Yet it is a reality unfolding before our very eyes. We have already seen the miraculous emergence of thought-controlled prosthetic limbs, where individuals who have lost an arm or a leg can, with focused intention, move a bionic limb as if it were their own. The signals from their motor cortex, once destined to move a biological hand that is no longer there, are now captured, decoded, and translated into precise commands for a robotic counterpart. Picture the profound liberation, the restoration of agency that such a technology offers. It is a testament to the brain's incredible plasticity, its willingness to adapt, to learn a new body, a new way of interacting with the world. Consider also those individuals who, due to devastating conditions like amyotrophic lateral sclerosis, ALS, or severe spinal cord injuries, find themselves locked in, fully conscious but unable to move or speak. For them, BCIs offer a voice where silence once reigned. Tiny electrodes, often implanted on or within the brain, pick up subtle shifts in neural activity, perhaps the imagined movement of a cursor or the intention to select a letter on a screen. These signals are then amplified and interpreted, allowing a mind trapped within its own body to communicate, to express thoughts, desires, even jokes. It is a profound reassertion of the self, a breaking of the invisible chains that bind. And we are not entirely new to the concept of directly influencing brain activity with technology. We spoke in Chapter 7 about the profound impact of deep brain stimulation, DBS, in treating conditions like Parkinson's disease, severe depression, and obsessive-compulsive disorder. Here, fine electrodes surgically placed in specific brain regions deliver controlled electrical pulses, modulating abnormal neural circuits. While not a BCI in the sense of reading thoughts to control external devices, DBS is a powerful example of neurotechnology's capacity to directly intervene with the brain's electrical symphony, restoring harmony where discord once prevailed. It highlights the delicate balance of neural activity and how targeted electrical pulses can bring about significant improvements in quality of life. But how do these incredible feats occur? At its core, it relies on the brain's fundamental language, electricity. Every thought, every sensation, every movement is underpinned by the firing of neurons, tiny electrical pulses traveling across vast networks. BCIs work by detecting these electrical signals. Some systems, like electroencephalography, EEG, place sensors on the scalp, picking up the collective electrical activity of millions of neurons. These are non-invasive and easy to use, though their signal is broad and diffuse. More precise systems involve surgically implanting electrodes directly onto the brain's surface, electrocorticography, ECOG, or even into the brain tissue itself. These invasive methods offer higher fidelity, capturing the signals from individual neurons or small clusters with remarkable clarity. Once these signals are captured, sophisticated algorithms, the digital translators of our age, come into play. They learn to recognize patterns in your brain activity that correspond to specific intentions. If you imagine moving your right hand, for instance, a unique pattern of neural firing might emerge in your motor cortex. The algorithm learns this pattern and associates it with the command "move right." It's a beautiful dance between biological electricity and computational intelligence, a continuous feedback loop where your brain learns to generate clearer signals and the algorithm learns to interpret them more accurately. As we stand at this precipice, looking out at the vast potential, our minds naturally drift to what lies beyond the horizon. What if neurotechnology could do more than just restore lost function? What if it could enhance our capabilities? Imagine a future where BCIs could augment our cognitive functions, sharpening memory, extending attention spans, or even accelerating learning. Picture a student seamlessly accessing vast databases of information directly into their working memory, or an artist experiencing entirely new sensory inputs to inspire their creations. And then, the truly profound, almost mystical possibilities emerge. Could we one day achieve a form of shared consciousness? Imagine connecting directly to another mind, not through the clumsy medium of words, but through the direct exchange of thoughts, emotions, and even sensory experiences. What would it mean to truly feel another person's joy or sorrow? To see the world through their eyes? Or to collaborate on a complex idea not by speaking but by intertwining neural landscapes? This vision, while distant, forces us to confront the very nature of empathy and connection, pushing the boundaries of what it means to be an individual. But with such immense power comes profound questions, philosophical and ethical dilemmas that we as a society must begin to ponder now. If parts of our brain are augmented or replaced by technology, where does I begin and the machine end? Does our sense of self, our unique identity, become blurred? If our memories can be uploaded, downloaded, or even edited, what happens to the authenticity of our personal history, the very narrative that defines us? Consider the question of autonomy and control. Who owns the data generated by our thoughts? Who controls the interface? What if a BCI could be hacked or influenced by external forces, subtly altering our perceptions or intentions? These are not mere technical challenges. They are fundamental questions about human agency and freedom. And what of equity? If advanced neurotechnology offers unparalleled advantages in cognitive ability or physical restoration, will it create a new divide, deepening the chasm between those who can afford such enhancements and those who cannot? Will a neuro-elite emerge, fundamentally altering the competitive landscape of human achievement and even defining what it means to be fully human? These are not questions for scientists alone, but for philosophers, ethicists, policymakers, and indeed, for all of us. As we gaze into this future, we are reminded yet again of the profound mystery that lies at the heart of our exploration. Even as we learn to read the brain's electrical signals with increasing precision, even as we build bridges between mind and machine, the subjective experience, the qualia of seeing red, the feeling of love, the sense of being, remains elusive. We can observe the neural correlates of consciousness, we can even influence them, but the leap from electrical activity to lived experience is still the grandest, most beautiful enigma of all. Neurotechnology is not just about wires and algorithms, it is about extending the very essence of human potential, about healing, connecting, and perhaps, in the distant future, redefining what it means to exist. It forces us to confront our deepest fears and our highest aspirations. It is a journey that demands not only scientific rigor, but also profound wisdom and ethical foresight. As we conclude this chapter, I invite you to hold on to this sense of wonder, tempered by thoughtful contemplation. The brain, this inner universe, continues to surprise and inspire us. And now, as we begin to build pathways directly into its intricate landscape, we are not just exploring the brain, we are exploring the future of humanity itself. The journey into the mind, it seems, is far from over. Indeed, in many ways, it has only just begun. And so, my dear friends, we arrive at a precipice. We have journeyed through the intricate landscapes of the brain, from the elegant dance of individual neurons to the grand orchestration of neural networks that give rise to thought, emotion, and memory. We've explored the very frontiers of neurotechnology, envisioning a future where the mind might interface directly with machines, extending our capabilities in ways once thought unimaginable. Yet, after all this exploration, after dissecting the brain's every known function and mechanism, we find ourselves standing before the greatest enigma of all. This is the ultimate frontier, the profound mystery that underpins every sensation, every thought, every dream we've discussed so far. It is the question of consciousness itself. How does this symphony of electrical impulses and chemical exchanges, this complex biological machinery we call the brain, give rise to the subjective, vivid, undeniable experience of being? How do physical processes translate into the feeling of seeing the color blue, of hearing a melody, of tasting a sweet fruit, or of loving another human being. This is what philosophers call the hard problem of consciousness, and it remains truly the most captivating challenge in all of neuroscience. We've seen how the attention acts as a spotlight, how perception actively constructs our reality, and how the sense of self emerges from a continuous narrative woven from memories, emotions, and interactions. But these are descriptions of what happens, of the brain's incredible processing power. They don't fully explain the why or the how of subjective experience, the what it's like to be you right now experiencing these words. Imagine for a moment that we could perfectly map every single neuron in your brain, charting every connection, tracking every action potential, monitoring every neurotransmitter release. Even with this impossibly detailed blueprint, would we then understand why you feel what you feel? Why you have a unique inner world? Or would we simply have an incredibly complex machine, albeit one that perfectly simulates human behavior? This is the core of the mystery. Many of us in neuroscience operate under the framework of materialism or physicalism, believing that consciousness is an emergent property of the brain. This perspective suggests that just as the wetness of water emerges from the interaction of individual H2O molecules, consciousness emerges from the incredibly complex interactions of billions of neurons. No single neuron is conscious, nor is a small cluster, but when they reach a certain level of organization and complexity, voila, consciousness appears. It's like a complex melody emerging from the individual notes played by an orchestra. The melody isn't in any single instrument, but in their collective intricate interplay. This view finds strength in the undeniable correlation between brain activity and conscious experience. When specific brain regions are damaged, specific aspects of consciousness can be altered or lost. When we administer certain chemicals, consciousness shifts dramatically. When we stimulate particular areas, sensations arise. The evidence strongly suggests that the brain is not just necessary for consciousness, but intimately involved in its very generation. We observe the neural correlates of consciousness, the specific patterns of brain activity that reliably accompany conscious experience. But identifying these correlates is not the same as explaining how they produce the experience itself. It's like knowing which parts of a car move when it drives, without understanding the internal combustion engine's fundamental principle. So we ask, what is it about these complex neural networks that gives rise to qualia, the raw subjective qualities of experience? The redness of red, the taste of chocolate, the ache of a broken heart. These are not merely data points, they are felt experiences. A computer can process data about the wavelength of light that creates red, but does it experience redness? We have no reason to believe it does, and this is where the hard problem truly bites. We can explain the information processing, the decision-making, the behavior, but the subjective first-person phenomenal experience remains elusive. Some theories attempt to bridge this gap, offering frameworks for understanding how consciousness might arise from information to processing. One prominent theory, Integrated Information Theory (EIT), proposed by Giulio Tononi, suggests that consciousness is a measure of a system's capacity to integrate information. A system is conscious to the extent that it has a large repertoire of discriminable states, information, and that these states are causally integrated within the system, meaning the system is irreducible to its parts. In essence, the more a system is able to generate and integrate information about itself and its environment, the more conscious it is. It's a fascinating, mathematically rigorous approach suggesting that consciousness isn't just on or off, but exists along a spectrum, and that the brain, with its vast interconnectedness, is a prime example of a highly integrated system. Another influential idea is global workspace theory, GWT, championed by Bernard Baars and Stanislas Dehaene. This theory posits that consciousness arises when information, initially processed by specialized non-conscious modules, comes globally broadcast to a wide audience of other brain systems. Imagine your brain as a vast theatre. Many specialized processors are working backstage doing their jobs non-consciously. But when certain information is important enough, it's brought onto the stage of the global workspace, illuminated by the spotlight of attention and made available to the entire audience of other cognitive processes. This global broadcasting, this widespread availability of information, is what we experience as consciousness. It helps explain why we're only conscious of a fraction of the information our brains process, and why attention plays such a crucial role. Yet even these sophisticated theories, while offering compelling models for the structure or function of consciousness, still grapple with the leap from objective process to subjective experience. They explain how information might be processed in a way that correlates with consciousness, but the why it feels like something question lingers. Historically, dualism proposed that the mind and body are fundamentally separate entities, with the mind being non-physical. While largely out of favour in modern neuroscience due to its lack of empirical testability and its struggle to explain how a non-physical mind could interact with a physical brain, it reflects the intuitive difficulty many people have in reconciling subjective experience with purely material processes. More recently, some speculative ideas like panpsychism suggest that consciousness, or proto-consciousness, might be a fundamental property of all matter, existing even at the subatomic level, and that our human consciousness is simply a more complex manifestation of this pervasive property. While intriguing, these concepts push the boundaries of what is currently scientifically testable. So where does this leave us, you and I, in our quest to understand the brain? It leaves us with profound humility and an even deeper sense of wonder. The brain is the most complex object in the known universe, and consciousness its most enigmatic product. It is the very foundation of our existence, our perception of reality, our sense of identity, the I that perceives, that thinks, that feels, that remembers, that dreams. This I is inextricably linked to the intricate workings of this 3-pound organ. The ongoing scientific pursuit of consciousness is not just an academic exercise, it is a journey into the very heart of what it means to be human. It touches upon questions of free will, morality, identity, and even the nature of reality itself. If consciousness is entirely an emergent property of the brain, what implications does that have for our understanding of self and agency? If we could one day create artificial intelligence that genuinely experiences qualia, what would that mean for our definition of life and personhood? These are not easy questions, and they are certainly not questions we can fully answer today. But the beauty lies in the asking, in the relentless pursuit of understanding. Every new discovery about neural networks, about information integration, about the precise timing of brain activity, brings us a step closer to illuminating this darkest corner of our own inner universe. For now, we embrace the mystery. We marvel at the fact that within the confines of our skulls, a universe of subjective experience unfolds. We are, each of us, a testament to the brain's incredible capacity not just to process information, but to generate a vivid, unique, and deeply personal reality. And as we conclude this journey through the fundamentals of neuroscience, I invite you to carry this sense of wonder forward. Look at the world, look at yourself with new eyes, recognizing the silent symphony of your brain constantly working to create the masterpiece that is your conscious experience. The journey continues, and perhaps one day you will be among those who help illuminate this ultimate frontier. Welcome back, dear friends, to Dreamy Academy. As the twilight deepens around us, we find ourselves at the culmination of an extraordinary journey, a journey that has taken us from the silent symphony of individual neurons to the grand, interconnected architecture of the human brain. We've explored the electrical whispers that spark thought, the chemical dances that shape emotion, the intricate mechanics of memory, and the boundless potential of neurotechnology. We've marveled at the brain's plasticity, its capacity for adaptation, and its remarkable ability to construct our perception of reality. And yet, as we stand here, gazing out at the vast, shimmering expanse of what we now understand, a profound question, a luminous mystery, continues to beckon from the deepest shadows. It is a question that underlies every synapse fired, every memory formed, every emotion felt, and every technological marvel conceived. It is the ultimate frontier, the very heart of our exploration. How does the physical brain give rise to subjective experience? We've delved into the brain's easy problems, as some call them. We've mapped the neural correlates of consciousness, identifying which brain regions activate when you see a face, feel pain, or recall a memory. We understand the complex computations involved in processing sensory input, in directing attention, in generating motor commands. We can trace the pathways of information flow, predict behavioral responses, and even, through BCIs, begin to interact with these intricate systems. But I ask you, does knowing where and how these processes occur truly explain what it's like to experience them? This, my friends, is the hard problem of consciousness. It's the chasm between the objective physical description of brain activity and the subjective qualitative experience of being. Imagine for a moment the vibrant crimson of a sunset, the sweet melody of a favourite song, the poignant ache of longing, or the crisp taste of a freshly picked apple. We can describe the wavelengths of light hitting the retina, the vibrations reaching the cochlea, the hormonal surges in the limbic system, the molecular interactions on the taste buds. We can chart the electrical impulses travelling through your neural networks. But how do these objective physical events transform into the subjective experience of redness, of sweetness, of melancholy? How does the firing of neurons become the private, ineffable feeling of being you, right here, right now? This is the enigma of qualia, the raw, irreducible elements of our conscious experience. Consider the rich tapestry of your inner world, the warmth of a memory, the texture of a dream, the unique flavour of your own thoughts. These are not merely data points or computational outputs, they are felt, lived realities. We understand that light-sensitive cells in your retina convert photons into electrical signals, which then travel through complex visual pathways to your occipital lobe. We know that these signals are processed, interpreted, and integrated with past experiences, but the experience of seeing the colour blue, that specific unique blue, seems to transcend the mere sum of its physical parts. It is a private theatre, a personal symphony, playing only for you, and it's not just about individual sensations. The hard problem extends to the very fabric of our being, the unified sense of self. We are, each of us, a continuous narrative, an I that persists through time even as every cell in our body, every thought in our mind is in constant flux. Billions of neurons, each a tiny independent processor, fire and communicate in a dazzling, chaotic dance. Yet from this immense distributed activity, a singular, coherent awareness emerges. Where is the conductor of this silent symphony? Where is the central command center that stitches together sights, sounds, thoughts, and feelings into the seamless ongoing story of you? The truth, as far as we understand it, is that there is no single dedicated consciousness center in the brain. Instead, consciousness appears to be an emergent property arising from the complex, dynamic interactions across vast networks of neurons. It's like the intricate patterns that emerge in a murmuration of starlings. No single bird dictates the overall shape, but the collective interaction creates something far grander and more beautiful than any individual component. Yet even with this understanding, the how remains elusive. How does this emergence translate into subjectivity? How do these patterns generate the feeling of being a starling soaring through the sky? Philosophers and neuroscientists have grappled with this question for centuries, proposing various theories that attempt to bridge the gap. Some suggest that consciousness arises from the brain's ability to integrate vast amounts of information into a unified whole, a concept explored by integrated information theory. Others propose a global workspace theory, where information becomes conscious when it is broadcast to a wide range of brain regions, making it globally available for processing. These theories offer powerful frameworks for understanding the functional aspects of consciousness, what it does, but they still struggle to explain the qualitative, what it's like. They describe the mechanisms, but the magic of the experience remains just beyond our grasp. Indeed, much of what our brain accomplishes operates outside the realm of our conscious awareness. Think of the intricate processes that maintain your heartbeat, regulate your breathing, or filter the vast torrent of sensory information bombarding you every second. Your brain is a tireless, largely unconscious architect, building the very reality you perceive before it even reaches your conscious spotlight. We only become aware of a tiny fraction of its immense activity. Thus, what is it about that small fraction that allows it to break through the veil of unconscious processing and become the vivid, personal experience we call consciousness? What is the unique quality, the special resonance that elevates mere information processing into felt experience? This profound mystery carries with it immense philosophical implications. If consciousness is merely an emergent property of complex physical systems, what does that mean for concepts like free will, personal identity, and the very purpose of existence? If our subjective reality is a product of electrochemical reactions, does that diminish its beauty, its meaning, its profundity? Or does it conversely imbue the physical universe with an even greater sense of wonder, revealing that the very fabric of reality holds the potential for self-awareness, for feeling, for knowing? As we stand at this precipice of understanding, looking into the abyss of the unknown, we are not met with despair, but with an exhilarating sense of possibility. The hard problem of consciousness is not a wall. It is the most exciting, challenging, and deeply personal frontier in all of science. It invites us to push the boundaries of our knowledge, to develop new tools, new theories, and perhaps even new ways of thinking about reality itself. It forces us to confront our own assumptions, to question the very nature of what it means to be alive, to be human. The journey we've shared through Dreamy Academy has been one of illumination, peeling back layers of complexity to reveal the intricate elegance of the brain. But it has also been a journey of humility, reminding us that the greatest mysteries often lie at the heart of what we think we know best. The brain, this 3-pound universe nestled within our skulls, is not merely a biological machine. It is the vessel of our dreams, our fears, our love, our creativity, and our unique, subjective experience of the world. So, as we conclude this particular chapter, I invite you to carry this sense of wonder forward. Continue to question, continue to explore, and continue to marvel at the extraordinary enigma that is consciousness. For in that quiet, persistent questioning, in that profound appreciation for the unknown, lies the true spirit of discovery. The brain is not just something we study. It is the very instrument through which we study, the very lens through which we perceive. And the mystery of how it creates our subjective world remains the most captivating story of all. Thank you for joining us on this incredible exploration. May your nights be filled with thoughtful dreams and your days with renewed curiosity about the silent symphony playing within you. Good night from Dreamy Academy.